I am Wensong, a research associate professor at NC State University. It is my pleasure to report the progress of resonant converter for EV charger using 3.3 kV and 700 volt silicon carbide MOSFETs. Freedom System Center at NC State University is focusing on intelligent power and energy management using wide bandgap power electronics. The key objective of this project is to develop a Technical Readiness Level 5 resonant isolated DC-DC converter with 30 kW power for EV charger using TO247 cost-effective 3.3 kV and 700 volt silicon carbide MOSFET devices. The system peak efficiency will reach 97.5% at 200 kHz switching frequency. Power density is targeted at 4 kW per liter, which is 5 times better over 3.3 kV silicon IGBT solution. Detailed reference design will be documented for resonant converter with high power, high frequency, and high control bandwidth. A practical example will be demonstrated to leverage 3.3 kV and 700 volt silicon carbide MOSFETs for system cost reduction. For the proposed system configuration, a fully functional resonant power hardware is integrated with digital control firmware for a 30 kW EV charger using 3.3 kV and 700 volt silicon carbide MOSFET devices. Digital multi-loop control with advanced path frequency and path width modulation is proposed to improve efficiency, stability, and control bandwidth. High voltage silicon carbide MOSFET operating at a high frequency to reduce the size and the cost, while improving the system performance, is the key technical approach. Full range of zero voltage soft switching is guaranteed even under the condition of zero load. Cost-effective TO247 devices are co-designed with aluminum nitride double-side cooling. This is a critical enabling technology to make a high-voltage silicon carbide implemented with much lower cost and better thermal performance. 3.3 kV silicon carbide MOS operating at 200 kHz enables 16 times reduction of our transformer volume compared to silicon IGBT solution. The innovative, cost-effective 3.3 kV silicon carbide assembly is shown in this figure. High performance and low cost assembly of full bridge 3.3 kV silicon carbide MOSFETs is co-designed with aluminum nitride thermal interface, PCB-based busbar, local ceramic dislink capacitor, rubber buffer layer, and cold plate with cooling channel. Thermal simulation using Solidworks verified that a 3.3 kV silicon carbide MOSFET can be integrated with cooling channel of 700 volt silicon carbide devices to improve the power density and reduce the system cost. Unclamped inductor switching test of a Microsemi 3.3 kV silicon carbide MOSFET was conducted to verify the robustness and voltage handling capability of the high voltage silicon carbide MOSFET. A simple LC series resonant testbed is proposed to test high voltage silicon carbide devices operating at zero voltage switching with the desired voltage, current, and switching frequency. The testing waveforms verifies that the 3.3 kV silicon carbide MOSFET is capable of operating at 200 kHz, 26 ampere, and 2 kV voltage. Virtual prototype of a 30 kW resonant converter is a very useful tool to visualize the high performance of the proposed design. It shows that the converter power density is up to 6 kW per liter, which is 1.5 times better than the required metrics. An innovative digital control for resonant converter is proposed and implemented. Variable frequency with pulse width modulation technology is developed to realize better controllability of a resonant converter with adaptability to load and voltage variations. The detailed volume distribution of 30 kW power converter is given in this figure. The dominant volume of components are the heat sink of silicon carbide power devices and the transformers. The total power loss of a converter at 30 kW and 500 volt is estimated at 371 watts, and the converter efficiency is up to 98.8%, even with 200 kHz switching frequency. This table listed the estimated cost breakdown. Total cost for 30 kW output power is $2,080. The cost per kilowatt is about $70. It demonstrated the proposed 3.3 kV silicon carbide EV charger solution is cost effective while achieving high efficiency and high power density. In conclusion, 3.3 kV silicon carbide MOSFET can be operated at 200 kHz high frequency with the rated voltage and current. High voltage silicon carbide devices will not only reduce the size of power electronics and improve the energy efficiency, but also reduce the system cost by the proposed system integration of a circuit topology, digital control, and TO247 package. We will provide a detailed reference design and report more testing results in open source manner to the Power America Institute partners and industry members for further commercialization and mass production. Thank you.